Imagine, just for a second, that you are actually standing on the surface of Mars.
Right.
The sky above you is this weird, dusty butterscotch color. The temperature right outside your pressure suit is hovering somewhere around like -80 degrees Fahrenheit.
Freezing.
Yeah, totally freezing. And you pull out a communication device, you type out a really simple text message to your family back on Earth, and you hit send. And then, well, you wait.
And wait.
Exactly. You just stand there in the dead silence of this alien world. And depending on where the planets are, it could take up to 20 minutes for that signal, traveling at the literal speed of light, just across all that empty, irradiated space.
It's just massive distance.
Right. Then it's another 20 minutes just for their reply to reach you. So, I mean, a simple "how are you doing" takes nearly an hour of dead air. So the big question is, how does a society survive or, operate and govern itself when that umbilical cord to the home planet is stretched that thin? When you can't just joystick a landing from Houston or call an ambulance or order a replacement microchip with next-day delivery.
I mean, the psychological and operational weight of that delay is just staggering. Because the moment you introduce that level of isolation, the entire paradigm of human survival has to shift.
Right, it's a totally different game.
Absolutely. You aren't just camping out in an extreme environment. You are actively fighting a thermodynamic and biological reality that, well, it wants to kill you every single second.
Yeah.
And you're doing it, for all practical purposes, entirely alone. The safety net is just gone.
And that unimaginable challenge, right, severing the safety net and trying to build a new one on another world, that is the focal point of our deep dive today. We're looking at the intense engineering vision and obviously the cold, hard reality of getting to Mars. And to guide this exploration, we are using the book Elon Musk by Walter Isaacson. Now, before we take another step, I really need to be explicitly clear about the parameters of what we're doing here.
Super important.
Yeah. This deep dive is an independent Cosmora HQ book overview. This production is not a complete book narration. It's not an official audiobook. It is not an adaptation, an abridgment, a technical endorsement, or in any way a substitute for the original biography.
Right. That distinction is just paramount because we are using Walter Isaacson's biography as a lens to examine a very specific culture of innovation.
Exactly.
We're looking at the raw mechanics of leadership, extreme manufacturing pressure, risk tolerance, and just huge technological ambition. But we're pulling back from the biographical narrative, to look at the massive underlying architecture of interplanetary travel.
Right, which brings us to the central question framing this entire deep dive today. Can reusable rockets, artificial intelligence, and radical engineering turn interplanetary civilization from an aspiration into a practical future?
And to answer that responsibly, we are enforcing some really strict scientific evidence controls on this discussion.
Yeah, weigh those out for us.
Well, we aren't doing a personality-driven celebrity profile, right?
Yeah.
We aren't just walking through the book chapter by chapter. The aerospace industry is kind of notorious for blurring the lines between a really cool rendering and actual flying hardware.
Oh, for sure. The CGI always looks flawless.
Right. So every technological claim we discuss today will be rigorously categorized. We'll identify if a technology is demonstrated, meaning, it works right now in reality.
Got it.
We'll note if it's currently in testing. We will clarify if it's an officially proposed architecture, if it's a broad aspirational goal, or if it is entirely speculative. Because when you're talking about Mars, the gap between a sleek computer render and a demonstrated system
is measured in decades.
Decades, billions of dollars, and occasionally human lives.
So true. Okay, let's start by looking at the philosophical engine that's driving all this hardware. You hear this phrase constantly in Silicon Valley and in the aerospace sector. First principles reasoning.
Right, the famous buzzword.
Exactly. It sounds like this ultimate intellectual trump card. But what are we actually talking about when we apply first principles to orbital mechanics and metallurgy?
So, stripped of all the corporate jargon, first principles reasoning is essentially a physics-based approach to problem solving, instead of reasoning by analogy.
Which means what, exactly?
Which means looking at how rockets were built in the 1980s and just trying to make them, like, 10% cheaper.
Ah, okay. Incremental change.
Exactly. Instead of that, you boil the problem down to the fundamental truths of physics and chemistry. You ask, what are the absolute minimum physical requirements to accelerate a payload to orbital velocity?
So you're stripping away all the assumptions.
Yes. You look at the specific impulse of propellants, the mass fraction of the vehicle, and the raw elemental costs.
So you basically go down to the commodity level, you look at a rocket and say, okay, this isn't some magical artifact. It is a structure made of aerospace-grade aluminum, titanium, copper wiring, and carbon composites.
Exactly.
And then you check the spot price of those raw materials on the global commodities market, and you compare that raw cost to the price tag of a finished legacy rocket component from, a traditional defense contractor.
Right. And when you do that, the difference is often shocking.
Like, completely out of whack.
Totally. The difference between the raw material cost and the finished component exposes decades of historical bureaucracy, legacy supply chains, cost-plus contracting models, and institutional risk aversion.
Right, because the traditional aerospace industry was basically built during the Cold War and the Apollo era.
Yes, exactly. And it was incentivized to prioritize absolute performance and zero-defect manufacturing over cost efficiency. First principles thinking kind of cuts through that historical cruft. It demands that every single dollar spent is justified by physics, not by tradition.
Okay, I totally get the appeal of that. You wiped the slate clean. But I have to push back here because this sounds like a massive double-edged sword.
How so?
Well, let's look at mature fields, right? Like commercial aviation or legacy spaceflight. The assumptions they operate on aren't just arbitrary rules made up by bureaucrats in the 1970s. Those safety standards, all those massive redundancies, they are quite literally written in blood.
Very true.
They're the result of catastrophic failures. So how do you balance this aggressive desire to break historical assumptions with the absolute necessity of respecting the hard-won lessons of past engineering tragedies?
Honestly, that tension is the defining characteristic of modern aerospace engineering. First principles calculations have really severe limits.
Okay.
Because a spreadsheet can tell you the theoretical ideal, right? It can tell you the most efficient thermodynamic cycle for a rocket engine. But a calculation cannot predict the chaotic reality of the physical world. It just can't fully model complex thermal behaviors or microscopic acoustic vibrations ripping through a fuel manifold or, bizarre, unpredictable software interactions under extreme G-forces.
So the math says it works, but the metal disagrees.
The metal always gets the final vote. Always.
Wow.
And this is exactly why first principles must be paired with empirical iteration. You have to build the hardware, subject it to the real world, and gather data. A spreadsheet won't tell you how a specific titanium valve will behave when it's simultaneously blasted with cryogenic liquid methane on the inside and the acoustic shockwave of 33 engines on the outside.
Yeah, you just have to blow it up a few times to find out.
Exactly. That requires physical testing, and it's crucial to understand that this level of engineering is not the product of a solitary genius sketching on a napkin.
Right, which brings up a really mandatory clarification we need to make based on our sources. The biography obviously centers on Elon Musk, and we need to accurately describe his role in this ecosystem.
Yes, we do.
He is the founder of SpaceX, and he is a technology entrepreneur deeply involved in major artificial intelligence ventures, from the early days of OpenAI to xAI. But we must be absolutely clear about the scope of that involvement.
We must. The whole notion of the lone inventor is this persistent myth, but it is entirely inaccurate. Elon Musk is not the founder, he is not the inventor, and he is not the sole creator of artificial intelligence.
Right.
Artificial intelligence is this vast, multifaceted discipline that has evolved over more than half a century. It rests on the foundational mathematics, computational theories, and neural network architectures developed by literally thousands of researchers, academic institutions, open source communities, and massive public agencies.
And, the same applies to the rockets themselves, right? First principles and high-risk tolerance might set the corporate direction, sure. But the hardware that actually achieves orbit is the culmination of a massive distributed network of collective achievement.
Absolutely. It's thousands of structural engineers, metallurgists, software developers, and aerodynamicists doing the actual mathematical and physical labor.
Yeah.
Furthermore, the entire private space industry relies heavily on the foundational legacy data provided by NASA. It relies on launch infrastructure built by the public sector, and it operates under the rigorous safety oversight of agencies like the FAA.
So if we're going to understand the path to an interplanetary future, we have to acknowledge that it requires the mobilized expertise of an entire civilization, not just one individual company.
Exactly.
Okay, so taking that collective reality into account, let's look at the most glaring inefficiency of the 20th century space program. If you apply a first principles analysis to the Apollo or the space shuttle eras, the economics are just baffling.
You really are.
We spent millions, sometimes billions of dollars building these incredibly intricate skyscraper-sized machines filled with precision machine engines. We flew them exactly once for a few minutes and then intentionally dropped them into the ocean to sink.
It is an economic model that guarantees spaceflight will remain a rare, bespoke activity.
Yeah.
I mean, imagine if commercial aviation worked that way.
Oh, yeah.
Imagine flying a Boeing 747 from New York to London, and upon landing at Heathrow, everyone disembarks, and they just push the airplane into the ocean.
The cost of a single ticket would be astronomical.
Exactly. The core thesis of the interplanetary vision, like the only way the math even begins to work, is reusability.
But let's apply our labels here, right? Because the aerospace industry loves to talk about reusability as if it's a solved, universal absolute. So what is strictly demonstrated today?
What is demonstrated repeatedly and with high reliability is the ability to recover and reuse the first stage of the Falcon 9 rocket.
Okay.
SpaceX has routinely launched payloads, separated their massive first-stage booster, performed complex retropropulsion maneuvers in the upper atmosphere, deployed aerodynamic grid fins to steer the falling cylinder, and landed it vertically on an autonomous drone ship in the ocean or back at the launch site.
Which is still just visually unbelievable.
It's incredible, and this is a demonstrated operational fact. And it fundamentally alters launch economics because you are amortizing the massive manufacturing cost of the main engines and the airframe across 10, 15, or 20 flights.
Right. That is an incredible engineering triumph. But, and this is a really crucial distinction, the Falcon 9 represents partial reuse.
Correct.
The upper stage, the part that actually pushes the satellite into its final orbit, still burns up in the atmosphere. The architecture required for Mars, the Starship system detailed in the biography, is completely different. The reusability model for Starship is currently in testing and officially proposed. It is not yet a demonstrated commercial reality.
That's right. Starship proposes complete, rapid reuse of both the Super Heavy booster and the upper stage spacecraft itself. Nothing is thrown away.
Okay, catching a falling booster is mind-blowing. It's like throwing a javelin into the sky and catching it perfectly as it falls, but rapid reuse. That takes the javelin analogy and just stretches it to the breaking point. Well, rapid reuse means catching that thrown javelin, handing it right back to the thrower, and expecting them to launch it again perfectly a dozen times a day without ever stopping to, X-ray the wood for stress fractures.
That analogy perfectly illustrates the hidden compounding costs of rapid. Because the word reusable does not automatically mean cheap, and it certainly doesn't mean easy.
Right.
The leap from catching a booster once a month to turning around a massive orbital vehicle in a matter of hours requires an industrial revolution on the ground.
What are those hidden costs, though? Because the fuel itself is relatively cheap, isn't it?
Oh, yeah. The marginal cost of the liquid oxygen and methane is a tiny fraction of the launch cost. The real expense lies in the infrastructure. Full, rapid reuse requires unprecedented fleet sizes.
Meaning you need a lot of rockets.
Right. You cannot operate a Mars logistics chain with 2 rockets.
Oh.
You need a conveyor belt of hundreds of vehicles. Building that fleet requires factory throughput that resembles automotive manufacturing way more than traditional aerospace. Furthermore, the launch pad infrastructure takes a brutal beating. The acoustic shockwave and the thermal exhaust of 33 Raptor engines will just vaporize regular concrete. The pad has to be robust enough to survive the launch and immediately be ready to catch and refuel the next vehicle.
And think about the maintenance. I mean, anyone who has flown commercially knows about airplane maintenance checks. Commercial jets undergo rigorous A, B, C, and D checks where airframes are literally stripped down to inspect for microscopic metal fatigue.
Exactly.
So if you're flying an orbital spacecraft rapidly, you have to develop non-destructive inspection techniques that can verify the structural integrity of the entire vehicle in, what, hours?
Yes. You have to check thousands of thermal protection tiles. You have to inspect engine turbopumps that were just subjected to extreme cryogenic cold and blazing combustion heat.
And then there's the sheer scale of the propellant logistics.
Oh, the logistics are insane. A fully stacked Starship requires thousands of tons of super-chilled cryogenic fluids. Sourcing, transporting, storing, and rapidly loading that much liquid oxygen and methane multiple times a day.
Yeah.
It requires a ground supply chain that is just mind-boggling.
Yeah.
The factory, the pipelines, the tank farms, that entire ground-based ecosystem is the hidden denominator in the launch economics equation.
So, okay, assuming the economics of rapid reuse are solved, right?
Yeah.
And we can launch massive payloads into low Earth orbit cheaply, how do we actually get that massive payload across the Gulf of space to Mars?
That's the real trick.
Right. This leads us to the proposed interplanetary architecture. And again, let's keep our evidence controls really strict here. This entire sequence we're about to discuss is currently officially proposed and in testing. None of this is demonstrated.
The foundational reality of the Starship architecture is that physics is a harsh mistress.
Yeah, it doesn't care about your business model.
No, it doesn't. The Starship vehicle is massive. It's designed to carry over 100 metric tons of cargo. But because of the immense energy required just to escape Earth's gravity well, the vehicle uses up nearly all of its propellant just reaching low Earth orbit.
So it's essentially running on fumes by the time it reaches space. It can't go anywhere else without a fill-up.
Precisely. And this necessitates orbital refueling. The officially proposed architecture involves launching a fully loaded Mars-bound Starship into orbit. Then, you launch a coordinated campaign of tanker Starships vehicles modified purely to carry extra fuel.
Okay.
These tankers must rendezvous with the Mars ship while traveling at 17,500 miles per hour, dock securely, and transfer their cryogenic propellants.
I really want to pause here and dig into the sheer mechanical terror of this idea.
It's a lot.
Trying to refuel a fighter jet midair is dangerous enough, but doing it with massive skyscraper-sized silos filled with boiling, sloshing cryogenic liquids in the microgravity of space? I mean, the physics of fluid dynamics in zero-G are notoriously hostile. Liquids don't just sit nicely at the bottom of a tank, they just float around in blobs. How do you even pump it?
It's incredibly difficult. Managing fluid dynamics in microgravity requires complex solutions, like using small thrusters to create a tiny bit of artificial gravity.
Just by pushing forward a little bit.
Exactly. It's called an ullage maneuver, and you do it just to settle the liquid at the bottom of the tank so the pumps don't ingest helium or gaseous bubbles, which would completely destroy the engines later.
Wow.
Furthermore, you are battling thermodynamics. Liquid oxygen and liquid methane must be kept incredibly cold. In orbit, one side of your spacecraft is baking in unfiltered solar radiation, while the other side is exposed to the deep freeze of deep space.
So the fuel literally wants to boil off into gas.
Exactly. Managing that boil-off, maintaining the thermodynamic stability of the transfer, and ensuring the absolute purity of the propellants over a campaign of multiple launches are staggering engineering hurdles that are currently deep in the research and development phase.
And let's talk about the compounded risk of that campaign. The sources suggest that fully loading a single Mars-bound Starship might require somewhere between 5 to 10 tanker launches.
Yes.
Think about the launch windows. If a Mars departure requires 10 flawless orbital rendezvous and refueling operations within a span of a few weeks, aren't we multiplying the risk of mission failure exponentially?
Math says yes.
Right. Like a single delay, a weather issue in Texas, a stuck valve on a tanker, a docking misalignment in orbit could cause the Mars ship to miss its planetary alignment window entirely?
That is the fragile underbelly of a highly dependent architecture. You're moving away from the risk of a single monolithic launch event, like the Saturn V going to the moon, and relying instead on the compounding probability of a complex logistical chain.
Every link in that chain must hold.
Every single one.
Let's shift to the chemistry of the fuel itself, because it's a huge part of the Mars plan. SpaceX chose liquid methane and liquid oxygen for the Raptor engines. Historically, we've used highly refined kerosene, like in the Falcon 9, or liquid hydrogen, like the Space Shuttle. So why methane?
There are two primary drivers for methane. The first is operational. Methane burns much cleaner than kerosene.
Cleaner how?
Well, kerosene combustion leaves behind this sticky carbon soot residue inside the engine plumbing, a process known as coking. If your goal is rapid reusability, you cannot afford to take an engine apart and scrub the soot out of the turbopumps after every single flight. Methane engines theoretically require far less refurbishment.
Okay, that makes total sense for the Earth side. But the second reason moves us firmly into the aspirational category, right? In situ resource utilization, living off the land.
Yes, ISRU. The long-term aspirational vision is to manufacture the return propellant actually on the surface of Mars.
No.
Mars has an atmosphere composed of about 95% carbon dioxide. We also have extensive geological evidence of water ice buried beneath the Martian regolith.
The dirt.
Yeah, the dirt. If you can mine the water and capture the atmospheric carbon dioxide, you can use a well-understood chemical process called the Sabatier reaction. By applying high heat and a catalyst, you can react the carbon dioxide and hydrogen from the water to produce pure methane and water. You then separate the oxygen from the water, and boom, you have your liquid rocket fuel.
Let's just break down the sheer audacity of what you just described. The Sabatier reaction works beautifully in a controlled laboratory on Earth, but let's look at the mechanisms required to do this on Mars.
It's a heavy lift.
You have to land autonomous mining robots on a hostile planet. They have to dig through frozen, abrasive dirt to extract ice. You have to land massive atmospheric processing plants to compress a freezing atmosphere that is 100 times thinner than Earth's.
Right.
You have to run the Sabatier reactors, which require massive amounts of continuous electrical power. You have to liquefy the resulting gases and store them in cryogenic vats for months without them boiling away. And finally, before you load that fuel into a rocket and strap human beings on top of it, you need an automated way to verify the absolute chemical purity of the propellant.
Because if there's even a trace of contamination in that methane, the turbopumps will cavitate and explode.
Exactly. Which is exactly why ISRU on a planetary scale is firmly labeled as aspirational. It requires an industrial supply chain that we honestly haven't even mastered on Earth, operating autonomously millions of miles away.
That's spot on.
And we haven't even touched on the most physically brutal part of the journey: entry, descent, and landing.
Yes.
Mars is famously referred to as the graveyard of spacecraft. It presents a thermodynamic nightmare. Why is it so hard to land a heavy payload on Mars?
It is the ultimate Goldilocks problem, inverted. The Martian atmosphere is roughly 1% the density of Earth's, so it is far too thin to use parachutes to brake a massive 100-ton vehicle. There simply isn't enough air resistance.
Okay.
However, it is substantial enough that when a vehicle hits that atmosphere at interplanetary velocities upwards of 17,000 miles per hour, the kinetic energy compresses the gas in front of the ship, generating immense aerodynamic stress and horrific heat.
So you're slamming into a wall of air so hard, you ignite the atmosphere around you into a plasma, but the air isn't thick enough to actually stop you before you hit the ground.
That is the exact physics of it. A vehicle like Starship must use aerodynamic braking, essentially performing a controlled belly flop, using its heat shield to bleed off as much speed as possible. But because the air is so thin, it will still be falling at supersonic speeds as it approaches the ground.
Terrifying.
Yeah, and at the very last possible moment, it must execute a complex maneuver to flip itself vertical, ignite its main engines, and perform a propulsive pinpoint landing to reach zero velocity right at the surface.
I mean, humanity has successfully landed one-ton robotic rovers using those complex sky crane systems, right? But landing a vehicle the size of an office building filled with delicate cargo or human crews, that requires dynamic performance and thermal survival that is just an order of magnitude beyond anything in the historical record.
Oh, without question.
So how do you cross that chasm? How do you go from whiteboards and CAD models to an office building that can do a supersonic backflip on another planet?
You test.
You test constantly and you test aggressively. Which brings us to the culture of innovation described in Isaacson's biography, the tension between hardware-rich testing and human safety.
Yes. The developmental methodology heavily utilized by SpaceX relies on rapid build-test-learn cycles. The underlying philosophy is that a physical test flight, even one that ends in destruction, provides exponentially more valuable data than years of theoretical computer modeling. By pushing a physical prototype to its breaking point, you accurately map its structural margins. You discover the unknown unknowns, how the software interacts with a sticking valve, or how a specific weld behaves under extreme cryogenic cycling.
You build it, you fly it, it explodes over the Gulf of Mexico, and you learn from the debris. It's the move fast and break things mantra applied to heavy industry. But our sources are very clear on a vital caveat here. Blowing up a rocket is only useful if you know why it blew up.
Absolutely. A spectacular explosion without high-fidelity telemetry is just expensive fireworks.
Yeah.
The iteration only works if you have thousands of sensors streaming data back and a culture rigorously dedicated to root cause analysis.
Yeah.
You have to trace the failure back to the exact line of code or the specific bolt that sheared.
I understand the value of that for uncrewed development. It totally makes sense when you're launching welded steel prototypes over an empty stretch of coastline. But I have to ask a foundational question about organizational DNA here. When a company eventually transitions from expendable cargo prototypes to human-rated operations, doesn't that culture of acceptable explosions have to fundamentally rewire itself? You can't preach zero tolerance for error when human lives are aboard if your institutional muscle memory is built on, let's launch it and see what breaks.
That transition is the human-rated barrier, and it is a monumental, often painful leap for any aerospace organization. The risk posture must shift entirely. What is an acceptable learning opportunity for a test article is a catastrophic tragedy for a crewed mission.
Exactly.
Human rating a vehicle demands layers of complexity that test flights just do not. It demands instantaneous escape capabilities. It requires intricate fault tolerance, meaning if a primary computer fails, a secondary system seamlessly takes over without dropping a single millisecond of telemetry. It requires exhaustive abort logic.
It's the difference between something working once on a good day and something working hundreds of times in terrible conditions without ever failing fatally.
Yes, cumulative reliability. And this introduces the danger of schedule pressure.
Oh, yeah.
Intense, aggressive deadlines can brilliantly focus a team's energy. But history shows us that schedule pressure can also create a normalization of deviance.
Normalization of deviance, like accepting things that are actually broken.
Right. If a culture values speed and launch cadence above all else, engineers might begin to rationalize away weak signals. Oh, that sensor reading was slightly out of bounds, but it didn't cause an abort last time, so it's probably just a glitch. Keep going. We have seen that exact psychological trap lead to the loss of the Space Shuttle Challenger and Columbia.
Which is exactly why the controls around innovation are as important as the innovation itself. A culture capable of safely managing deep space travel must have rock-solid organizational channels for informed dissent.
Absolutely.
It must mandate anomaly reporting, encourage independent review, and fiercely protect stop-work authority. The technician on the floor who pulls the alarm and halts a launch because a flange doesn't look right must be celebrated just as much as the engineer who designs a more efficient engine. You have to move rapidly where failures are contained and observable, but you must meticulously slow down where human consequence is high.
Very well said.
Okay, let's assume we navigate that cultural shift. We have the rockets, the testing culture is mature, and we are ready to operate. Now we need to look at the brains of the operation. Because, returning to our opening scenario of a 20-minute communication delay, mission control in Houston or Hawthorne cannot fly the mission.
They cannot.
They cannot instantly read telemetry and manually troubleshoot a failing oxygen scrubber. That physical distance makes artificial intelligence not just a nice upgrade, but an absolute operational necessity.
Right, because the speed of light is the ultimate unbreakable constraint of deep space exploration. It mandates local autonomy. Mars-bound spacecraft and surface habitats must be able to ingest massive amounts of sensor data, detect emerging hazards, prioritize their own communications to Earth, and, most critically, maintain safe operational states locally without waiting for human permission. So let's cut through the sci-fi hype. Using our labels, what are the realistic, demonstrated, or in testing roles for AI in this architecture? One of the most mature applications is predictive maintenance. A Mars settlement is essentially a giant, complex machine. It relies on thousands of pumps, compressors, fans, and rovers. Machine learning models excel at analyzing continuous streams of time series data. They can monitor the acoustic and thermal signatures of a water pump and detect the subtle, microscopic vibrations of a failing ball bearing weeks or months before the pump actually seizes up.
That is massive. Because on Mars, if a pump breaks, you can't run to the hardware store for a replacement. You have to know it's going to fail so you can machine a new part in advance. What about physical robotics?
Robotic site preparation is highly realistic and currently in testing and development. Before human crews risk the journey, we must send autonomous robots to scout and map landing zones.
Right, to pave the way.
Yeah. These machines will need advanced computer vision and spatial awareness to grade uneven terrain, navigate around boulders, deploy acres of delicate solar arrays, and begin assembling foundational habitat structures, all while recovering from their own slip-ups in the Martian dust without humans joysticking their every move.
Okay, those are powerful tools. But I want to push back hard on the idea of trusting algorithms with survival because AI has a very specific Achilles heel. Let's look at the false positive versus false negative dilemma.
Okay, let's do it.
If an AI monitoring life support flags a false positive like, it confidently announces that a critical air valve is about to fail, but it's actually perfectly fine. You've just forced an exhausted, radiation-dosed crew to waste precious hours suiting up, conducting a dangerous spacewalk, and replacing a good part.
A massive waste of physical and psychological resources.
But the alternative is worse. A false negative. The AI system says everything is green, but the valve is actually failing, means the crew suffocates in their sleep. When you can't just hit Control-Alt-Delete and call tech support, how do you possibly calibrate trust in a machine learning model?
You've hit on the exact reason why we must define the limits of AI and heavily restrict the speculative fantasies. AI cannot, and fundamentally should not, replace verified deterministic control systems in life or death scenarios.
Break that down for me. What is the difference between an AI and a deterministic system?
A deterministic system is governed by hard-coded, physics-based, immutable rules. If it receives input A, it will absolutely always execute output B. If the pressure in an oxygen tank exceeds a specific mathematical threshold, a mechanical relief valve opens. Period.
No guessing.
There is zero probability involved. Artificial intelligence, particularly modern neural networks, operates on probabilities and pattern recognition. It is incredible at finding signals in noisy data, but it is also capable of hallucinating.
Right.
It can confidently provide a completely incorrect answer, especially if it encounters an edge case scenario it was never trained on, like a bizarre combination of radiation-flipped bits and extreme thermal cycling.
A hallucinating AI in a medical emergency is terrifying. Oh, I've analyzed the patient's symptoms and determined you need to perform an appendectomy using a soldering iron.
Precisely why the architecture must enforce strictly bounded authority. The AI serves as an advisory layer. It might synthesize millions of data points and recommend a course of action. I detect an anomaly in the thermal regulation loop. I suggest routing coolant to the backup radiator.
But it doesn't just do it on its own.
Exactly. It does not possess the authority to unilaterally execute that command without human confirmation or an underlying deterministic safety check. Furthermore, we cannot overlook the sheer vulnerability of software. Cybersecurity in space is paramount.
Because someone could hack the life support.
Yes. When software controls your propulsion, your atmospheric pressure, and your water supply, those systems must be air-gapped and hardened against manipulated inputs, corrupted updates, or single-event upsets caused by cosmic rays.
All right, we've analyzed the rockets, the testing philosophy, the communication delays, and the software. But we are avoiding the most fragile, unpredictable, and vulnerable component in this entire interplanetary architecture.
Us.
Yeah. It isn't made of forged steel, carbon fiber, or silicon. It is made of meat. It's us. Arriving on Mars is a profound engineering achievement. Surviving on Mars is a grinding, unrelenting biological crisis.
NASA identifies 5 major hazards for human spaceflight. These are not minor details to be figured out after the rockets are built. They are the fundamental constraints that dictate the design of the entire architecture. We call them the Big Five.
Let's walk through them and let's really go deep into the biology. Hazard number 1 is the invisible killer, radiation.
On Earth, our biology evolved under the protective blanket of a thick atmosphere and a powerful planetary magnetic field that deflects the vast majority of space radiation. The moment you leave low Earth orbit, that shield is gone.
Just completely exposed.
Right. Crews traveling to Mars are bombarded by galactic cosmic rays, high-energy protons, and atomic nuclei traveling near the speed of light, originating from supernovae outside our solar system. Additionally, they face the unpredictable, massive doses of radiation from solar particle events or solar flares.
Let's talk about what that actually does to a human body, because these aren't just intense sunburns.
No, not at all. When high-energy cosmic rays strike the human body, they literally tear through cells on a molecular level. They ionize the water in our cells, creating highly reactive free radicals that can physically sever the double helix of our DNA.
Oh, wow.
This massive cellular damage significantly increases the lifetime risk of various cancers, damages the central nervous system, and during a severe solar storm can cause acute radiation sickness, which involves severe nausea, immune system collapse, and internal bleeding.
So how do you engineer a solution? I mean, you can't just wrap the spaceship in lead, right?
Actually, using heavy metals like lead is often worse.
Wait, really? Why?
Because when a high-energy cosmic ray hits a dense metal atom, it shatters the nucleus, creating a shower of secondary radiation shrapnel that is even more damaging to the crew.
Oh, that's wild.
The best shielding materials are actually rich in hydrogen like water, or specialized polyethylene plastics. The hydrogen atoms absorb the impact more cleanly, but surrounding a spacecraft's living quarters in thick layers of water adds immense mass. And in rocketry, mass is the ultimate enemy.
Right.
Furthermore, the long-term biological effects of sustained exposure to this specific cocktail of deep space radiation remain one of the biggest unknowns in space medicine.
Okay, so that's radiation. Hazard number 2, altered gravity.
The transit to Mars takes roughly 6 to 9 months, during which the crew experiences microgravity. Without the constant mechanical stress of gravity pulling on the body, the human machine rapidly adapts, but in ways that are detrimental for planetary exploration.
Like losing bone mass.
Yes, bones lose calcium and density, becoming brittle. Muscle mass atrophies. The cardiovascular system weakens because the heart doesn't have to pump against gravity. Fluid shifts upward into the head, which increases intracranial pressure and frequently flattens the shape of the eyeball, causing permanent vision degradation.
We have astronauts on the International Space Station who deal with this, right?
Yes, and their primary countermeasure is intense, hours-long exercise every single day using massive resistance machines. But those treadmills and resistance devices consume vital volume and electrical power on a spacecraft. And the gravity problem doesn't end when you land.
Because Mars only has partial gravity.
Exactly. Mars possesses only 38% of Earth's gravity. We simply do not have the long-term empirical data to know if a human body can maintain healthy bone regeneration, cardiovascular fitness, or reproductive viability while living in partial gravity for years or decades.
Hazard number 3 is distance and isolation, but let's look at it specifically through a medical lens.
The sheer distance forces radical medical autonomy. On the ISS, if an astronaut suffers a severe medical emergency, a heart attack, a ruptured appendix, or a toxic chemical exposure, they can be loaded into a Soyuz or Dragon capsule and be in an advanced hospital on Earth within a matter of hours.
Where there's a lifeboat.
On Mars, evacuation is physically impossible. The orbital dynamics do not allow it. Therefore, the crew must be capable of performing advanced, complex medicine entirely on their own. They must execute diagnostics, complex surgical interventions, and pharmacological treatments using only the highly restricted mass of equipment they brought with them, all without the ability to consult a specialist on Earth in real time.
You literally have to know how to perform a root canal, set a complex bone fracture, and manage an infectious disease outbreak, all while living in a tin can.
Yes.
Which brings us to hazard number 4, closed environments.
A Mars habitat is not a building. It is a complex machine that you live inside. Survival relies on a series of aggressively closed-loop life support systems. You are continuously scrubbing carbon dioxide from the air. You are capturing and recycling every single drop of moisture, from atmospheric humidity to crew sweat to urine, running it through complex filtration and chemical processing, and returning it as drinking water.
The coffee you drink today is quite literally the coffee you drank yesterday.
Exactly. And the hazards in a closed environment go far beyond the pumps and filters breaking down. When you seal humans in a pressurized container, the microbiology changes. Bacteria and fungi mutate in altered gravity and radiation. The materials of the habitat itself, plastics, adhesives, electronic components, slowly off-gas toxic volatile organic compounds that must be scrubbed.
And what about the dirt outside?
You have the constant threat of Martian dust, which is incredibly fine, highly abrasive, and chemically reactive due to perchlorates in the soil. It will inevitably get tracked inside on spacesuits and inhaled. But the most terrifying apocalyptic hazard in a closed environment is fire. If an electrical fire breaks out in a Mars habitat, you cannot simply open a window to vent the toxic smoke.
You are trapped in a sealed tube with poisonous gas.
Yes. A settlement cannot depend on flawless hardware indefinitely. Filters will clog. Microbes will breach the water lines. The environmental engineering must be phenomenally robust and easily repairable by exhausted humans wearing thick gloves.
This brings me to the 5th hazard, which often gets glossed over in the glossy presentations. The psychological reality. I want listeners to really try to internalize the sheer existential weight of this. Imagine putting on your suit, stepping out of the airloft, and looking up into the Martian night sky. You search the stars, and you find a tiny pale blue dot. That tiny dot is Earth.
It's hard to fathom.
Every human being you have ever known, every tree, every ocean, every breeze, every piece of music ever written, the entirety of human history is trapped on that single dot. And you are tens of millions of miles away, standing in freezing, irradiated dust. We talk endlessly about hardware repairability, how to machine a new impeller for a water pump. But how do you repair the human psyche when a crew member truly absorbs the reality that there is absolutely no possibility of a rescue mission?
It's the great wild card.
How do you engineer resilience against a level of profound, sensory-deprived isolation that no human being has ever experienced?
And it is a question that fluid dynamics and metallurgy cannot answer. We can attempt to mitigate it through rigorous psychological screening of astronaut candidates. We can implement AI-assisted behavioral health monitoring to detect the subtle vocal or facial cues of depression or psychosis. We can try to design habitats that incorporate virtual reality or biophilic design to simulate nature.
But predicting how a human mind will actually handle it.
Predicting how a mind will fracture under the sustained multi-year pressure of planetary isolation remains beyond our current models. The human element is the ultimate single point of failure in the interplanetary architecture.
which means that keeping those highly fragile humans physically and psychologically intact requires a massive, continuous, unbreakable logistical chain. This isn't the Apollo program where you plant a flag, pick up some rocks, and go home 3 days later. A permanent Mars city is, as the sources emphasize, a continuing production system. Let's move into economics and logistics.
The most critical distinction we must make here is separating the demonstrated capability of landing a vehicle on Mars from the deeply aspirational goal of achieving a self-sustaining civilization. Self-sufficiency is not a binary state. It is a spectrum spanning centuries.
Let's explore that spectrum, because it's easy to say, oh, we'll just live off the land. Sure, you might successfully deploy a Sabatier reactor to generate oxygen. You might set up a complex hydroponic bay and grow a reliable crop of genetically modified potatoes. But what happens when the highly complex photolithography-etched microchip that controls the thermal regulation of your water recycler burns out?
Or what happens when a crew member develops a highly specific bacterial infection, and you need a complex antibiotic that cannot be synthesized from Martian regolith?
You die, unless you have a resupply.
For decades, and perhaps for the first century of a Mars settlement, the outpost will remain completely dependent on Earth for high-value, complex manufacturing. They will need a continuous pipeline of advanced electronics, specialized medical pharmacology, complex diagnostic tools, and the highly specific replacement parts for the automation systems that keep them alive.
And shipping that is not cheap.
Every single kilogram of cargo sent from Earth is breathtakingly expensive. Reusable rockets like Starship may radically lower the transport barrier, but they do not make the advanced microchips, the MRI machines, or the pharmaceutical labs themselves any cheaper.
So before human beings even begin to pack their bags for a permanent stay, we have to prepare the planet. We touched on robotic site prep, but let's dive into the ultimate logistical bottleneck of any civilization: power.
Nothing happens without massive amounts of electrical power. Running life support, extracting water from ice, heating the habitats against negative 80-degree temperatures, running the propellant plants, communicating with Earth, it all demands constant, unrelenting energy.
And the easiest way is solar, right?
The easiest technology to deploy is solar power. But solar panels on Mars face severe limitations. They are hindered by the Martian latitude, the changing seasons, and most critically, the global dust storms. Mars periodically experiences planet-wide dust storms that can obscure the sun for weeks or months at a time.
That is exactly what killed NASA's Opportunity rover. The dust blocked the sun, the batteries drained, and the heaters failed.
Precisely. If you are relying purely on solar power, a global dust storm is an extinction-level event for a human settlement. The required alternative is nuclear fission reactors. But deploying nuclear power introduces a labyrinth of terrestrial policy hurdles, massive launch safety regulations, and significant mass penalties.
And everything has to work together.
Regardless of how the power is generated, the surface logistics will require absolute, rigid interoperability standards. A settlement cannot survive if it operates a fleet of incompatible, proprietary robots. You cannot have a situation where the battery module from cargo rover A doesn't physically fit into the power bus of Habitat B. Survival demands universal modular design, standardized connectors, and radical, simple repairability.
Okay, I understand the logistical mechanics, but let me challenge the core economic motivation underpinning this entire endeavor, because this is the massive elephant in the room that often gets ignored by space enthusiasts.
I know where you're going with this.
Beyond the pure spirit of human exploration, the pursuit of scientific discovery, and the geopolitical prestige of planting a flag, there is currently no established, profitable business case for a Mars economy. You are not going to mine iron or platinum on Mars and ship it back to Earth. The transport costs obliterate the commodity value.
That's entirely true.
So if the public funding from governments dries up, or if the backing of billionaires shifts to a new obsession, what happens? Does the Martian supply chain just stop? Are we risking the creation of a multi-billion-dollar company town in space that goes bankrupt and leaves its employees stranded to suffocate on another planet?
That is arguably the most sobering question of this entire deep dive, and it transitions us perfectly into our final area of analysis. Because if a permanent settlement actually manages to survive the radiation, navigate the psychological isolation, and maintain the complex supply chain, it suddenly ceases to be just an engineering project. It becomes a society.
And human societies require laws. Let's look at ethics, governance, and planetary protection.
Let's start with planetary protection. Because before we govern the humans, we have an international legal obligation to govern how we treat the planet itself. Under international law, Specifically, treaties like the Outer Space Treaty, spacefaring nations have a legal obligation to prevent the harmful contamination of celestial bodies.
Because Mars is a science lab.
Mars is considered a pristine scientific environment. The primary scientific objective of sending probes to Mars is to search for biosignatures, signs of past or present extraterrestrial life.
The problem is human beings are incredibly dirty. We are basically walking ecosystems of microbes.
We are. It is physically impossible to completely sterilize a human mission. We constantly shed skin cells, bacteria, fungi, and viruses. The moment a human boot steps onto the Martian surface, we introduce Earth biology to the environment.
Which ruins the science.
This severely complicates the scientific search for Martian life. If we find a microbe near the habitat, did we discover Martian life? Or did we just find a mutated stowaway from the astronaut's digestive tract? This reality will likely force strict international zoning standards. There may be intense debates declaring that human operations are restricted to specific regions, while other pristine areas are cordoned off as absolute exclusion zones for robotic science only.
And then we face the incredibly thorny issue of governing the settlement itself. Our sources make a fantastic critical point here. A corporation's end-user license agreement or terms of service is not a constitutional governance structure.
It absolutely is not. The logistical reality of Mars concentrates power to an unprecedented degree. Imagine a settlement established and maintained by a private corporation. Who holds the ultimate emergency authority to allocate scarce resources? If a primary oxygen scrubber fails and the backup is damaged, who decides who gets to breathe the remaining air? What are the labor rights of the technicians who are maintaining the critical infrastructure? How are disputes, crimes, or breaches of contract resolved when you are tens of millions of miles away from a terrestrial court of law or a local police force?
Think about the privacy implications, too. If the habitat's survival relies on an omnipresent artificial intelligence monitoring efficiency, resource consumption, and safety protocols, the crew is essentially living in a high-tech panopticon.
Absolutely.
The AI knows exactly when you sleep, what your heart rate is, how much water you consume, and how efficiently you are performing your assigned tasks.
That is a recipe for a technological dystopia if left unchecked. AI systems utilized for resource allocation or performance assessment concentrate immense power in the hands of whoever controls the algorithm. A sustainable, ethical settlement requires a true constitutional governance structure.
What does that look like?
It must clearly define data privacy access, establish transparent appeals processes, mandate independent audits of life support algorithms, and ensure absolute human accountability. Operational efficiency and corporate productivity can never outweigh fundamental human rights, even on a dead planet.
I want to highlight the extreme power dynamic at play here. If the single entity that employs you is also the entity that controls the air you breathe, the water you drink, the thermal heating that keeps you from freezing to death, and the AI that monitors your every movement, how do you ensure that basic human agency isn't simply optimized out of existence for the sake of the company's bottom line?
It's a terrifying thought.
And what about the concept of informed consent? Do employees truly have the capacity to consent to these unprecedented risks? And what legal obligation does the organizing entity have to provide truthful, unvarnished, non-marketing disclosure of the very real dangers they face?
These are profound structural questions that require robust international legal frameworks, not just corporate policy manuals or improvisational rules made up by the first settlers. Furthermore, our sources emphasize a vital philosophical grounding. The ambition to become an interplanetary species must never be framed as a rationale for abandoning Earth.
Oh, absolutely not.
The technological leaps required to survive on Mars, perfectly closed-loop water recyclers, extreme high-density energy storage, robust predictive AI, and hyper-efficient agriculture are exactly the technologies needed to manage climate and resource crises on Earth. Earth remains humanity's only proven, fully functioning biosphere. It is our cradle and our primary responsibility.
So, after this massive journey, what does this all mean? We have traveled from the theoretical purity of first principles reasoning through the fiery, destructive reality of rapid rocket testing. We've examined the thermodynamic nightmares of orbital refueling and Martian atmospheric entry.
We covered a lot of ground.
We really did. We've stared down the terrifying biological realities of radiation and isolation. And finally, we've confronted the massive ethical complexities of governing a fragile outpost in the dark. Let's pull this vast architecture together into our final synthesis.
The most valuable, grounded conclusion we can draw from the evidence and from the limitations of the biography is that an interplanetary civilization will not simply spring into existence because of a single visionary hero or one brilliant invention. It is a massive, incredibly complex, highly dependent system.
It's a team effort.
Achieving it relies on rigorous scientific evidence, decades of foundational work by public agencies, massive international institutions, the unglamorous execution of repeated mundane operations, and a mature willingness to strictly separate inspiring corporate visions from completed engineering facts.
Reusable rockets like Starship are a foundational tool. Artificial intelligence models that can predict a failing water pump are a foundational tool. Rapid iteration is a powerful methodology.
Yes, but they are just tools. A rocket does not solve the biological destruction of cosmic radiation. An algorithm does not solve the psychological terror of total isolation. And engineering speed does not solve the ethics of governance and human rights. Isaacson's biography invites us to reflect on whether extreme drive and a high tolerance for risk are the necessary ingredients for extraordinary progress.
And what's the verdict?
The balanced, evidence-based answer is that urgency, pressure, and rapid iteration can be incredibly effective for bending metal and building hardware. But sustainable achievement, the actual reality of keeping human beings alive, sane, and thriving millions of miles from their home planet requires far more. It requires informed dissent, meticulous verification, deep empathy, uncompromising safety cultures, and robust institutions that are built to outlast any individual leader.
The ultimate practical test of this vision isn't just, can we land a rocket? It is, can thousands of tons of cargo arrive repeatedly and safely? Can energy remain constantly available through catastrophic dust storms? Can life support be repaired with a limited box of spares? And can human institutions handle conflict without violence when a psychological pressure is unimaginable?
That's the real test.
As promised at the start of our journey, we used the book Elon Musk by Walter Isaacson to explore these massive themes. And I will restate one final time that this deep dive is an independent Cosmora HQ book overview. We actively encourage you to obtain and read the original book legally to explore the intricate biographical narrative, the personal histories, and the corporate dramas for yourself.
The central question of our deep dive remains open, and perhaps it will remain open for decades. But I hope we have demonstrated that the question is becoming increasingly concrete. We are slowly, painfully moving from the realm of science fiction into the realm of extreme engineering reality. But the path is paved with staggering physical, biological, and societal dependencies.
We want to hear from you. The debate over how and if we should undertake this journey is one of the most important conversations of our century. We invite all our listeners to share your thoughts, challenge our assumptions, and ask questions in the comments below. Dive into the debate with us.
We'd love to hear it.
And as we finally close this deep dive, I want you to think back to that opening scenario. You are standing in the freezing red dust of Mars. You've sent your text message to Earth. You are waiting 20 minutes for the signal to cross the dark void. In that profound isolation, surrounded by humming machines that are actively keeping you alive against a hostile universe, consider the vast, fragile chain of technologies, chemical reactions, and human decisions that put you there. And I want to leave you with this exact question to ponder.
Think about this one.
Which factor is most important for making humanity interplanetary? Reusable rockets, trustworthy AI, autonomous Mars infrastructure, human health protection, reliable life support, or responsible governance?